So in this video, I'm going to be covering section 3-2 measures of variation. I'm actually going to break this section up into 5 videos. This is a rather large section, so I felt like instead of making one long video, I'm going to make it into 4 videos. So please do watch all 4 videos. So before we jump into the actual content, there's some pre-skill that if you haven't taken algebra or you haven't taken, or it's been a long time since you've taken basic mathematics, arithmetic, it's good that you know what some of these notation is. So for example, like the squaring notation, the squaring notation or the power notation. So stuff like this you have to know, and then the square root as well. So I'm just going to do a few of these. I'm not going to do all of them, but it's good practice. So let me show you guys how to do this in the TI-84. So 6 to the second power, that's how we pronounce this, or we can say 6 squared. That's equal to 6 times 6, right? Exponential exponent is repeated multiplication. So this is equal to 6, whatever this number is. This number is called a base, and then the exponent tells us how many times it shows up, right? So in this case, it's 36. Using the calculator, we can just we can do the following. We can press 6, and then we can press the square button right here. Yeah, that'd be 6 squared. Or we can do 6 and then press the caret button, this is a general exponent button, right? And you can specify your power. So you can do like 3, or in this case, we're going to do 2 because it's raised to the second power. So like that. So like something like negative 10 squared, you have to put it in parentheses. So let me show you. If you do negative 10 squared like this, it's not going to give you the correct answer. So that's going to give you negative 100, which is not the correct answer, because we know negative 10 squared is negative 10 times negative 10, and the product of two negatives is a positive, so we know we should get 100. So if you have something like this with parentheses, you have to put parentheses as well. So like that, and then square it, and that gives you 100. All right, so the square root is the inverse operation, if you will, of the squaring. So with the square root of 49, we would ask ourselves, well, what number squared gives us 49? And then whatever that is here, whatever value we come up with, that's the answer to the question of the square root of 49. So in that case, 7 squared is equal to 49. So the square root of 49 would be equal to 7. Or you can take the calculator. You can put it into the calculator. So the square root is right above the x squared in blue, where we'd press second x squared and then put the 49 in there. All right. Okay, so those are pre-skills. And this pre-skill is just evaluating expressions, inputting values into an expression. So I'll go ahead and do one quick one. So for example, in this case, we're given that x is equal to 36, y is equal to 4.1, and we want to evaluate these expressions with those values. So for the first one, we're just taking x and we're going to substitute it with the given value, 36. So that's going to be 36 plus 2 times y. So in that case, y is equal to 4.1. And we would just evaluate this on the calculator. So we'd go 36 plus 2 times 4.1, just like that. Press enter. So a lot of times you do have to be cognizant or be aware that sometimes you may have to put parentheses around certain expressions so that order of operation doesn't mess things up, right? So in this case, we didn't need parentheses because order of operation is going to do multiplication first and then add, right? Evaluate this, and then whatever product we get, we would add to 36, so it's not going to mess it up. But where you usually get into trouble is if a problem like something like this, number 11, where you have like division. This one probably won't give you that any problem, but then more complicated ones with fractions, you always want to be safe and put parentheses. So let me go ahead and work this one out. So k is equal to 2, and they're asking us to evaluate this expression. So we would go 1 minus 1 over 2 squared, right? And then we'd evaluate that. So if we did it by hand, which is not too difficult, we would get the following. We would get 1 minus 1 over 4. And we know that we need to get like denominator. So any whole number can be written as a fraction with a 1 as a denominator. So we need a common denominator between these two fractions to subtract fractions, right? So the common denominator would be 4. So 1 over 1 would be 4 over 4, right? So minus 1/4. And this would be, so once we have common denominators, we would just evaluate the numerator. So 4 minus 1 is 3, so 3 over 4, which is 0.75, right? So if you wanted to put this into the calculator, it's not too bad. So this is how you would do it. You would go 1 minus, and because there's a couple of operations going on here, it's always safe to put a set of parentheses just to kind of block itself off, kind of put itself in its own little world, so that you can evaluate that first, and then once you evaluate that, then we would subtract that answer from 1. So we would do 1 divided by, right, the fraction bar here, we're going to view it as division, 2 squared, and then close the parentheses. So that tells us we're going to perform operations on this, and once we get this value, then we're going to subtract it from 1. 0.75. Okay. So now let's jump right into the meat of the section. So measure of variation. So here's just a small problem or a preview problem that you can figure it out. So the question says find the mean exam score for each student, then compare the performances between the 3 students. So go ahead and press pause and calculate the mean of each of these students. I'll give you a couple of seconds. In a couple of seconds, I'm going to show you the answer, but go ahead and press pause and figure it out. So the mean of these 3 students is all 70. It was not done by mistake. This was done on purpose. Anna's score was 70. Bob's average score was 70. Cora's mean score was 70. But just looking at these numbers, or the way that they perform on each of these tests, you wouldn't say their performance was equal, right, or the same. Even though their mean was the same, you wouldn't say their performances are the same. You would look at Anna and you would say she's very consistent. She scored all the same scores, right? Very consistent, no variation. And then Bob is a little bit more inconsistent, or a little bit more variation. It's more spread out, right? Some in the 60s and then 3 of them in the 70s. And then Cora is very, very, the variation is very spread out, right? So there's a lot of spread out. So the lowest score was 35 and the highest score was 100. So that's exactly what we're going to talk about in this section. We're going to talk about variation. So we're going to look at 3 measures of variation. And measures of variation measures how spread out the data values are in a distribution. So for example, just going back to the 3 students here, this one there's no variation. There's some variation, but not a lot. This one, there's a lot of variation, right? So if we were going to quantify the variation, this would probably be 0, right? And then this one more than 0, and this one is a lot more than 0, right? So that's what we're going to do in this section. We're going to look at 3 measures of variation that's going to quantify how varied that's going to measure or explain the variation for a data set. So here in this slide, these are some notations that you have to know. So these notations you have to know throughout the entire semester. We talked about these 2 already. So I've categorized these. I put the statistics on the left and then the parameters on the right. If you guys remember, statistics are numerical values relating to a sample, whereas a parameter is numerical values relating to a population, right? So this is the population. Both of these are mean, but this is the sample mean, x bar, and this is the population mean, mu. And then the variance and the standard deviations are measures of variation. We'll talk about that more, but this is the sample variance, S squared. This is the population variance, sigma, lowercase sigma squared. And my PowerPoint here is not projecting correctly, but this should be a closed loop like that, just like this one right here. So sigma squared. And then the standard deviation is lowercase s, and the population standard deviation is sigma, the lowercase sigma. Notice how this was not done by an accident. Standard deviation and variance, the difference between their notation is that standard deviation is s and the variance is s squared. It's because if you know the standard deviation, to get the variance, you would square the standard deviation, right? So likewise with the population standard deviation and variance, if you know the population standard deviation, you would square it to find this population variance. Okay, so now let's kind of step back and look at things broadly. So measures of center from last time. Remember, we looked at 3 of them. We actually also looked at mid-range, but we're not going to talk about it in this section because it's really not that popular. So we have mean, median, and mode, right? Those are the 3 most popular measures of center. For measures of variation, we have 3 that we're going to talk about. We have the range, we have the standard deviation, which is very important, and the variance. The standard deviation is the most important measure of variation that we're going to talk about. And remember from last section, the mean is the most important measure of center. These 2 kind of go hand in hand. You need to know the mean to calculate the standard deviation. So they're kind of tied to the waist, so to speak. The variance is also important, but the standard deviation, it's a little bit more important. Let's kind of hit the easy one first for the measure of variation. So let's look at the range. So the range is very simple. It's just the maximum value minus the minimum. So for example, for these 3 students, the range for this one would be 0, right? 70 minus 70, 0. For Anna, 0. For Bob, so the largest value is 79 and the smallest is 60. So that's 79 minus 60 gives me 19. And then for Cora, we're going to do the same thing. So the largest value, the max is 100, the smallest is 35. So that's going to be 100 minus 35, which is 65. So notice how these values, these measures of variation, right, the range, does a pretty good job of quantifying the variation for each of the students, right? So 0, no variation, 19, and then 65. Now let's look at the standard deviation. Again, standard deviation is very important. It's the most important one, and we're going to talk about it throughout the entire semester. So you have to know the notations, and you have to understand what it is. So the standard deviation is a measure of how far data values are from the mean. See how it mentions the mean? It's because you need to know the mean to calculate the standard deviation. So this next statement I put in quotation. This is not an accurate statement. I'm sorry. Well, let me just read it. So think of the standard deviation as the average distance the data values are from the mean. So the average distance, the data values, so each of the data values are from the mean. This is not the definition or the exactness of the standard deviation, but this is how I like my students to think of the standard deviation. It's pretty close, but this is not mathematically, it's not how you calculate. It's not what the standard deviation is, but think of it as the average distance the data values are from the mean. So let me show you guys exactly how to calculate the standard deviation using the table. We have a formula for it too. The formula is not as easy to calculate, to use, but I want you guys to know how to use a table, to create a table and use it, right? So let's take a look at Bob. So Bob, these are Bob's score, and we want to calculate the standard deviation. So with the standard deviation, we're looking to calculate the average distance each of these values are from the mean, right? So we know that the mean was 70, right? We were given that initially when we calculated Bob's mean. And the goal with the standard deviation is we want to look at those distance, right? So these orange dots are these scores, and then the green dot is the mean. We want to look at these distances, and once we find all of the distances, we want to find the average, right? Calculate the average of all of these values, of all of these distance. So we're going to use a table that looks like this. There's going to be 3 columns. There's one more that I just haven't animated in, but just know there's another column that's going to be animated in. So on the first column, we're going to put the x's. So these are the values of the exam scores from Bob, and we can put it in any order. It doesn't matter. All right, so the deviations, what they are is the distance from the x to the mean. So symbolically, let's just say this was, a population, right? So these would be my x's. So the deviation would be x minus the population mean, right? Which would be 70 in this case. So for the first score would be 70 minus 79, and then 60 minus 70, and then 72 minus 70, and so on, right? So these would give us working these out would give us the kind of like the distance. Technically, they're not the distance. That's why we call it the deviations. But these are the deviations, right? But let's just call it quote unquote the distances, which is really not. But let's play along. So the first deviation would be 79 minus 70 would be 9, and then this would be negative 10, and right, and this would be positive 2. This would be 7, positive 7, and this one would be negative 8. So let's go ahead and animate all that in. So that's what the deviations are. So typically, if you want to find the average distance, you would then add up all the distances and divide by the number of values, right? But if you add up all these values, because some of these are negative, some are positive, they're just going to cancel each other out. So the deviations are going to cancel each other out. You're going to get 0, right? So it doesn't help at all. So statisticians, they just realize that, and they say, well, let's just get rid of the negatives by squaring it. So the next column, the third column, is a square deviation. So all we're going to do in that column is we're going to take the deviations here and we're going to square it. So for example, we're going to go 9 squared, negative 10 squared, 2 squared, 7 squared, negative 8 quantities squared, just like that, right? So if we work those out, so like for example, 9 squared is 9 times 9. That's going to be 81. Negative 10 squared is going to give you a positive 100, because remember, negative 10 squared is negative 10 times negative 10. So let me write it up here. So that's going to be negative 10 times negative 10. And a negative times a negative is 100, right? So the purpose of squaring these values was so that wherever we have negatives, they're going to become positives because we're squaring them. Just like this negative 8 squared is going to become a positive 64, right? So here's what we get. We get 81, 100, 4, 49, and 64. All right, so from here, now we're going to add the square deviation. So if you add them all up, you total them up, you're going to get 298. So 298, and again, the idea is we're trying to find the average distance from the mean, right? So then to find the average after we added these square deviations, we would divide by n. So here it should be a capital N because we're pretending that this is a population. So we would go 298 divided by 5 because there's 5 scores. And we'd get 59.6. So 59.6, is that our standard deviation? Again, standard deviation, the goal of the standard deviation is to find the average distance from the mean. This is actually not it because we squared these deviations or distances, right? So it's actually the average of the square deviations. So technically that's not right. But we have a special name for this value. We call that the variance. So we have the variance is the average of the square deviations. And so to get the standard deviation, because we squared these deviations to kind of work our way backwards or work our way back, we would square root the variance. So to get the standard deviation, we would square root 59.6, which is the variance, right? And if we round, we'd get 7.72. So we're rounding to 2 decimal places, we'd get that value, 7.72. All right, so it's again, it's no surprise that The notation for variance, in this case population variance, is sigma squared, and the notation for the standard deviation is sigma. And likewise with a sample, the sample variance is s squared, and s for the standard deviation. The reason why is because if we know the standard deviation, again, if we know the standard deviation, all we have to do is square it to get the variance, right? All we have to do is take that 7.72 and then square it to get the 59.6. Now, we don't get exactly that because this was rounded, but that's close enough, right? And vice versa, if we know the variance, to get to the standard deviation, use square root. Okay, so you got to be familiar with those two things. Now, this is figuring out the standard deviation and variance using the table. So I'm also going to show you an easier way to do it using the calculator. Right? So if you use a calculator, anytime you want to calculate the standard deviation and variance for a data set, you would just take this data set and input it into the calculator. Again, we're trying to find the standard deviation and variance for Bob's exam score. So we're not going to do any of this because we're going to use the calculator. So we're going to press stat, go into edit. I'm going to clear these lists and input the values that I want. Okay, so once you have it in there, always good practice to quit out of this and then go back to stat and then go to calc 1var stats. Right, so we're going to input L1 because that's where I put this list. So L1's already there. And make sure you delete L2 because we don't need it. We don't have an L2, or we don't have a frequency list in this case, right? So we're going to click calculate. And sure enough, so because we treated this like a population, the standard deviation is sigma. So that's 7.72. And let's pretend that we started with this. How would we get the 59.6? We would square this value, right? This sigma. So we would square 7.720 and whatnot. So one way you can do it is you can just take it out to like 5 decimal places and then square that value. So taking this out to 5 decimal places would be, let's see, 1, 2, 3, 4, 5. We would stop at the 0 and we would put in all those values up to the 0 and then square that, right? So let me go ahead and do that. So that's going to be 7.72010, right? And then square that. And notice how it is going to be 59.6. Another way you can do it is when you run 1var stats, after running 1var stats like this, all of these values are going to be stored in as a variable, and you can access those variables. So what do I mean by that? So if you click on vars for variable, and if you go to statistics, right, because it's stored under the statistics variable, you can call those values. So we're going to call sigma x, right, going down to 4, press enter, and then we can just square that. So we can go square, and then it gives us the exact 59.6. All right. So another thing you might wonder is, after calculating, running 1var stats, you might say, well, you know, how come the standard deviation for the sample standard deviation is different from the population standard deviation? So let me explain why. So for the population standard deviation, the formula, the notation for that would be the following, right? We did all of the x minus mu, which is the finding the deviations, right? That first column or that second column in our table. And then we would square those values to get rid of anything that's negative, right? We square all the values. And then we took the sum of the squared deviations. And then we divided by n, right? And then the last thing we did to find the standard deviation was we took the square root. So that's the notation for the population standard deviation. For the sample standard deviation, the formula is a little bit different. It starts very similar. You take x minus the mean, right, to find the deviations, and then you're going to square those deviations, and then you're going to sum up those deviations, And then instead of dividing by n for the sample standard deviation, so the formula for the sample standard deviation, we're going to divide by n, 1 less than n, or n minus 1. And then we take the square root. And that is exactly why when you run the function, you get two different answers, one for the sample standard deviation and one for the population standard deviation, because for the sample, we're dividing by 1 less than the sample size. Why do we do that? The simple answer is because when you go from a population and you collect a sample data, it's going to be less variation with a sample. So to compensate for that, we're going to divide by 1 less than n. Something that statisticians have agreed that works out a lot better. I'm not going to go into too much detail of the explanation other than to say that, and just know that whenever there's a difference in the value, if the problem is asking you to find a population standard deviation, it's one value, and then if it's a sample standard deviation, it's a different value. So you got to be aware, you got to be able to decide if the problem asks you to find standard deviation, you got to be able to decide whether it's a population or a sample in the problem, right? So depending on whether it's a sample or a population, you have to use, your output is different, or you have to, the formula is slightly different. So that concludes this video. Again, these videos are going to be for section 3-2. I'm going to break it up into 4 videos. In the next 3 videos, I'm going to talk about 3 ways which we're going to help make sense of the standard deviation. So there's 3 things we're going to look at. The first is the range rule of thumb, the empirical rule for bell-shaped distribution, and then the Chevy-Shebs theorem. All right, I'll see you guys in the next video.